So I typed this one out. You guys will have to give me a little feedback regarding the quality of what you can and cannot see on this video, and we'll see how this works. Otherwise, I might have to do some adjustment to make sure that you guys are able to view the video clearly. So I broke this one down. This is the beginning of chapter 4, which is on series and sequences, and these are the learning goals, the big goals for this whole unit. Those include arithmetic sequences and series, geometric sequences and series, and then those are in terms of sums, and then it gives you sums of those types of sequences. We're going to review permutations and combinations, counting principle, and then the big one, it seems to show up on most DP tests, which is the binomial theorem and how to use that efficiently to help you expand large large polynomials. So for today, we're going to focus on 4.1 sequences and what is a sequence and how do we describe them. So the goals for this series of videos are going to be able to define and determine if something is finite versus infinite, compare and contrast explicit versus recursive equations, and then part C, which is to derive the formula of the sum of the first n terms in the Fibonacci sequence, which is something most of us are familiar with. So previous knowledge we can connect this to is that anytime you have a list of numbers that we are looking at, generally there's some kind of pattern that we can associate with that list of numbers. Sometimes there's not, but for most of the examples we're going to look at this year, there is some pattern. Not always linear, not always exponential, but some kind of pattern in which we can analyze it. So these are some types of patterns. This one right here is 6, 12, 18, 24, 30. So when you look at this, you can tell that there's an additive relationship from step to step of 6, and then it doesn't have a dot, dot, dot at the end. That specific little dot, 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 that's actually a mathematical term, and it's called an ellipses. And this, because it does not have one of those, is finite, meaning that it ends. Here's one that grows multiplicatively by 3, and if I was going to describe this sequence, it would be 3 to the nth. And then this one does have the dot, dot, dot option, which means that I'm looking for another term, that I can plug in any number for n and output any number, which means that this does not have an end in mind, so it's infinite. Here's an example that's not linear nor exponential. It's 1 over x squared, so it's nice to look at something that doesn't necessarily fit in the little bubble that we have looked at in the past for sequences and series. This one is saying that I'm going to take x, and that number could be 1 or 2 or 3. There's supposed to be a dot, dot, dot there, you guys. Sorry, you can add that in. Dot, 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 all the way up to 10. And I'm going to plug that in and create the series. So, for example, the first number of this series would be 1 over 1 squared. So the first number would be 1. Then I would take 2 and plug it in. 1 over 2 squared is 1/4. 3 in here would be 1 over 3 squared, which would be 1/9, all the way up to, you could do the 4 and the 5 and the 6, but we're going to just say that this pattern continues until we reach the 10th number, which would be 1 over 10 squared, or 1 over 100. And this does have an end in mind. It's saying this sequence goes from here to here. So this is a finite sequence, a finite list of numbers. Okay. Here we're looking at just a general format where I have b sub 1 being the first term, b sub 2 being the second, b sub 3 being the third, dot, 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 all the way up to b sub n, which means that there's no end in mind. So this one is infinite. So goal number 1, finite versus infinite. Okay, so if it ends, it's a finite sequence. If it doesn't end, it is not a finite sequence, it's infinite. Okay. So we're going to compare and define explicit versus recursive equations. So an explicit equation has some kind of formula where I can input any term and immediately get a coinciding output. For any independent, I can plug in to some kind of function and it's going to spit out the output associated with it. Okay, so we're going to look at an example of that. So let's say I have a function that is linear, and you're going to hear the term arithmetic sequence quite a bit. Arithmetic sequence means that it has a linear type of association. Both of them mean that we're talking about an additive relationship. It's just a shift in terminology. So it wants us to find the first through the fifth term using this explicit sequence, which is fine. So let's say I plug in 1, I would get 5 plus 2, which is 7, and then 9, 11, 13, 15. Now I can plug in for every single one of those, or I can generate it by just adding that 2 from, sorry, this is not right, adding the 5. So I would plug in 1 for 5 and get 5 times 1 plus 2 is 7. 5 times 2 is 10. 12. Now we're actually adding 5 from step to step. So second, third, fourth, and fifth. Okay. So explicit. So let's say one more example. Let's find b sub 1 through b sub 5 for the sequence where b sub n is defined by taking 2 and subtracting 1 over n squared. So I can look at this and say that b sub 1 is going to be 2 minus, well look, this is very similar to the one we did up here. How convenient that that's already done for a few of them. 1 over 1 squared is just 1. All right. b sub 2 equals 2 minus 1/4, which is 1 3/4. b sub 3 is 2 minus 1 over 3 cubed, which is 1/9, which is going to be 1 and 8/9. b sub 4 is 2 minus 1/16, which is 1 15/16. And then b sub 5 would be 2 minus 1/25. So 1 and 24/25. Now just kind of a thought as we go out. Let's say I wanted to, for some reason, calculate b to a really, not a huge term. Let's choose something that's reasonable, like b sub 50. Could I do it without building from any of the previous terms? Yeah. So that's how I know I'm dealing with an explicit, is that I can go to any term that I'm interested in and immediately plug in that term number into a function and get out the output. So that's one of the characteristics of an exponential function. So if I were to plug in that 50, I would say that that is 2 minus 1 over 50 squared is 2,500. And so that would be 1 and 2, 4, 9, 9 out of 2, 5, 0, 0. So if I were to plug in a really, really large term, like a million or something like this, so as n is approaching infinity, the output of this function is going to get closer and closer and closer to 2 from the left. So it's kind of an idea that we're going to talk about later when we are doing calculus, but as the input of a term gets really, really large, am I approaching a specific number or am I approaching infinity? In this case, I am approaching a specific number, and that specific number would be 2. Okay, we're going to take a minute, pause, and then we're going to look at recursive functions and how to use a calculator, RTI Inspire, to define a recursive function.